gave a mass, take it to be M, you apply some force the direction and it's displaced, let's say X, towards a fixed point. Now the force, according to the Newton's second law, states that the acting force is equals to the opposing forces. So if we apply force here, then there will be some opposing force, and we are calling that Fm. The opposing force in this case here is Fm, and according to the Newton laws, we are saying the acting force is equal to Fm, that is the force which opposes the exerted force. So according to the second law of motion, we have this equation: mass multiplied by the acceleration, and acceleration is usually the change in velocity all over the change in time. The change in velocity u squared, the change of velocity, the dv squared all over dt. And this is because velocity is usually the change in velocity. So we have that. So mass is equals to that, and acceleration is equals to this. So it means helping mass on the side of mass, we say m d squared v dt. This is going to be our x. This is going to be our x. Our x is that. So we are looking for the velocity. We say velocity is equal to dx all over dt. Dx all over dt. So this is so that is the equation for the mass. So it is equals to d squared all over dt squared. So based on this, having a mass of m, we apply some force, then there is an external force that will act against this force. According to that Newton's, say the sum of the two forces, the two opposing forces, it's equals to 0. So that means when you apply, you say F equals to Fm, they're supposed to give you the cosine, they are equal. So if you do some subtraction, you will get 0. Now F is equal to mass multiplied by acceleration, according to the Newton's law. Second, and acceleration is equal to d squared all over dt squared multiplied by the displacement. So like that. Then we go to number 2, that is the spring. We have a spring like this, and then you apply some force here, and then it's extends by x, that fixed position. So x is the displacement, and there is a force which is applied here. Now this opposition actually that will give us spring constant, and here we use the Hooke's law. So there is a force which is acting against that, which we are going to call it, if we detect the spring to be K, then we are going to say Fk. So F A is equals to Fk. But according to the Hooke's law, we know force is directly proportional to the spring constant by the spring extension. And our extension here is extension, so the displacement for our case is x for the k. So in spring constant is equals to Fk, which is equals to kx. That is the for the spring. So this is the equation. Then number 3 is the dashboard. Is the damper. We apply some force here, and then we expect. This is an example of brakes. Usually the brakes. So when you push this, then we expect this to move with a certain velocity. It's going to move with a certain velocity, and also it's going to extend some distance, but it's going to be displaced. So on the dashboard, then we say Fb, which is the force which is against the applied force, is usually equals to the damping coefficients multiplied by the dv all over dt, and that is the equation for the damper. So as we have said, we've got 3 elements. We've got the mass, we have the spring, and we have the dashboard. Let's see an example. So, as you said, modeling is representing it with blocks for analyzing control systems. But here I say for to is when we are looking at the transfer functions. So we say the transfer function here, the transfer functions. For example, we have a spring. We have a spring like this, held at that fixed position. And you apply some force. It is displaced by x. We are applying that. So what will be the transfer function? The transfer function will be equals to, this is the applied force which acts as the input, and this one acts as the output. So the transfer function is the ratio of the output all over the input. So our output for our case is going to be x. Our input will be f of s. We were saying we represent this in Laplace transform. We represent such in Laplace transform. So let's look at one example. So this is an example of a control system modeling. It is on mechanical. So when we are doing this, then always we should look at the masses. So, and again you see where the force is applied from. So the force is applied down here. So usually when you are doing this, you consider the masses. So for our case, we've got two masses. We have M1 and we have M2. So we can start with M1. We can start with M1, and we draw a free moving body of M1. So this is going to be an M1, and we try to identify the forces which are acting. So there is this force which is acting, that is Ft, F of t. So we have F of t, which is displaced by x1. There is a force which is acting also, which is acting on it, which is opposite to this one. Opposite to this one, and this one is going to be B, that is a F B1. There is also this force of the spring. It is also acting against the applied force. It is going to be Fk1, and that is also force as per the mass M1, which we are going to call it F M1. So those are, we've got three forces which are acting against Fx. Now, so what we are going to say, this is the force which is against. So when you add these three forces and you subtract from F of t, then we are supposed to get 0 according to the second law of motion. So if you say F of t is equals to Fb1 plus Fk1 plus Fm1 is supposed to give us that equation. So we can substitute the formula. Fb1, so F of t is equals to this. So we are starting from here, and this one is hung between M1 and M2. This one is displaced by y2, and this one is displaced by, this is x, by this one is y1. So we are going to say b1 dt. This one is, we are going to start from x1 minus x2, then plus the spring. This spring is going to be k1 into x1 minus x2 plus the mass, which we are going to get, so plus m1 dv squared all over dt squared x1 minus x2. That one should give us the first equation. That one should give the first equation. That one should give the first equation. Now we go to M2, and M2, there are forces which are acting against it, and there are those ones which are acting on it, and there are those ones which are against. So we've got these forces, we have got this and this one, and we've got this one which is against this one and this one. So let's identify those forces which are acting against that. There are forces, these forces, there are two forces which is acting away. You can say this. This one is going to be Fk1, and the other one is Fkp1. then there are those ones which are acting against, which is going in another direction, and it is going to be FK2. Another one is this one, FB2, and another one is this one. So FM2, FM2. Then we can clear this. We can clear this, and then from our equations, we're going to write FK plus FB1 is going to be equal to FK2 plus FB2 plus FM2. So that is what we have. We can substitute the formula. So FK, this was our 1 for this. So now we are starting from here. Then we are going to say K1 into x2 minus x1 plus b1 tt x2 minus x1 is going to be equals to k2 x2 plus b2 d. This one is going to be x2 dt. And we can erase this, but we can have more spaces. So this one should give us equation 2. So equation 1 was ft, which was equals to b1 dx minus dA that over dt plus k1 into x1 minus x2 plus m1 d squared dt squared into x1 minus x2. And then the second equation was k1 into x1 is x2 minus x1 plus p1 into is b1 dt into x2 minus x1 should be equals to k x2 plus b2 dt x2. So we can take this to fit to Laplace transform by saying dt, we write s. If it is d dt squared, then we are going to say s is squared. This one is going to be our fs is going to be b1 s into x1 minus x2 plus k1 into x1 minus x2 plus m1 s squared into x1 minus x2. This is equation 3. After doing Laplace, then we go to this one. It's going to be k1 into x2 minus x1 plus b1 s into x2 minus x1 equals to k2 x2 plus b2 s x2. this gives us equation 4. That gives us equation 4. Gives us equation 4. So we are supposed to come up with the transfer functions of x1 and fs. We are supposed to come up with that. So that means we are going to get rid of x2. So we are going to get rid of that. And what we are going to do is that we are going to substitute. We are going to open the brackets. So we are going to have f of s is going to be equal to b1. We open the brackets. So there is x1 here, there is x1 there, there is x1 there. So we are going to get that one out. Say x1 into b1 s into 1. So we are going to get b1s equal to the other one. Going to get plus k1 for substituting k, then plus m1s squared. We close with bracket. And then there is also another one, which is there is also x. So x2 can also factorize x2, which we are going to get b1 s is going to be, this one is going to be minus the other one is plus k1, then the other one plus m1 s squared, like that. Then from here we can get the value of x2 by taking this one to the other side. Then we are going to get x a squared b1 s plus k1 plus m1 s squared, which is going to be equal to x1 into b1 s plus k plus m1 s squared minus f. So our x2 around is going to be x1 into b1 s plus k1 plus m1 s squared minus f, and you are going to divide by b1 s plus k1 plus m1 over s. Then now we use this one to substitute here. So again times x, you can substitute x from here to say x2 into k1 plus b1s and then minus, there is also x1 here, so x1 into k1 plus b1s is going to be equals to x2 into K2 plus D2 S. Close the bracket. Like that. So finally, when you do substitutions, we're going to get this. We're going to substitute this that x with this equation. And then from there, we look at the ratios. So let's look at also another simple one before we end up. df xy over f2. Step is that from here, and there is this body which is acted by, so there is a force which will be acted by the mass, and then there will be a force which will be acted by this. The displacement is this. So if you draw free form body M, then there will be forces which will be that force Ft, and there is force of the spring, which we are calling it Fk, and there is that force of the body, which we are calling it E. Now, if you add these two, we say Ft equals to Fk plus Fm. But for our case, the force is 0. So we are going to say 0 equals to Fk plus Fm. Going to say, start with this one, 0 over m, d squared all over dt squared x2 plus, we have k, and k is in between x1, x2, and x1. So we are going to say k into x2 minus x1, which is equals to 0. And then we go to the force. So we have F of t, which is acted by the spring. So we have the spring, which is x1, extended by x1, x2. We are going to use this one because we are looking at force. So we are going to say x1 minus x2. That will be the force that will be acted by that. So again, dt, taking it that one by placing it. So and this equation 1 and this one is equation 2. So we are going to say 0 equals to m s squared x2 plus k into x2 minus x1. That gives us the third equation. Now Ft, we are changing to Laplace, f of s k into x1 minus x2. That is equation 4. And since we are told to determine the transfer functions, that is in terms of x1 all over f of s, then it means we're going to determine to open the brackets using the fourth equation, and we are going to say f is equals to k x1 minus k